welcome to Physics Bootcamp. Could we go around real quick and let me know your names and your major?
Chad, physics.
Or
Daniel, physics.
Christine, physics.
Steven, I'm actually doing physics and mathematics.
I'm Courtney, I'm construction management.
okay.
I'm Max. I'm a musician.
Okay.
Josh, chemistry and chemical engineering.
Okay.
Alyssa, physics.
Okay.
Connor, physics.
Okay. Super.
I know, right? Music, what do you play?
I'm a percussionist.
Nice, me too. There we go.
Good. So you're here for kind of general interest?
Well, I need it for the degree when I transfer in the fall.
Okay. Okay. If you're not a physics major, talk to me after. Let's make sure you're in the right spot. And really glad to have all of you here. So Physics Bootcamp is a new course that we've been developing for a few years. This is the first time we've ever offered it in the spring. Enrollment's a little lower than we've had traditionally in our fall offerings, but that's okay. I mean, you'll all get a lot of good attention. And we're going to have a recitation once a week, which is one of the very important components of this course, where we're going to do an awful lot of problem-solving practice together. So let's talk for a few minutes about what sort of the layout and intention of the course is. Let me walk you through the syllabus. So my email address is there, jwalker@shsu.edu. That's the most convenient way to reach me. Please be sure that your university-linked email address is something that you're checking regularly. I will send mailings out through Blackboard, for example, which will go to the group. So course description. This course is essential to those students initiating a study of pre-engineering and physics. It provides familiarity with the core problem-solving tools that are required to survive the first 2 years of work in these majors. The presentation will take the form of direct and practical examples throughout. The weekly problem-solving recitation is integrated. There are no prereqs, and it's a 4-hour credit course including the lab. It's a very important addition to our curriculum, which serves as a new entry point for all incoming physics and pre-engineering majors. Our main goals with the course are the following. One, to offer students for whom physics or engineering is on the list of possible majors a chance to try it out with no prerequisites on coursework. And number two, to ensure that our incoming students have the required leveling in quantitative and computational skills to allow them to be successful once we start taking regular physics classes. So I think back to my time as an undergraduate in my first semester in college. And I thought that I might be interested in physics, and I'd read Stephen Hawking's coffee table book, or is that still something that's in, does everybody know about Stephen Hawking? He died a couple years back. So he has his book, A Brief History of Time, was kind of new at that point, and it was on the coffee table of everyone who exhibit their interest in the sciences, and my uncle had a copy of it, and I spent the night at his house. We would pass through Dallas-Fort Worth sometimes to take flights out of there at Burnham, Muslim, and I read it there from his kind of nightstand or coffee table, right? And, you know, I knew I had an interest in these things, and I thought I might be interested in kind of these deep puzzles and deep riddles of nature, but I didn't really know what it was that physicists did. And the truth is, the first couple of years, the things that we teach you are very different from what you read about in Dr. Hawking's book, right? But we kind of got to work our way there. I knew I might be interested in physics, but I didn't really know what it was. And one of the problems is that when you show up to college, usually you've got to take a few courses even to get ready to take your physics course, which is a lot to ask of somebody who wants to try to figure out if this is the right thing for them. So one of our goals here at SAM was to have this as a first semester availability for incoming physics students. And the ideal thing is you hit the ground, you show up at SAM, you say, I might be interested in physics or pre-engineering. This is where you get sent. And we can find out real quickly in partnership with you whether that's really the thing that you want to do once you kind of get your hands started. The other thing is, and this is a problem that's common to physics departments all across the country and engineering departments all across the country, is that students come in with very different levels of mathematical background from high school. Right? So what we want to do in the physics boot camp is teach you all of the math that you need for those first 2 years to be able to survive in your physics class. And we want to do it in the most entertaining way possible. We want to do it with the most interesting physics examples possible. And one of the neat things about it is that you may be surprised, we can actually take some of these wonderful advanced topics from quantum mechanics or relativity and bring them in. And you don't have to understand all the physics yet at this point, but we can bring them in and introduce them and use them as examples for a matrix problem you might be interested in, or a trigonometry problem you might be interested in. And bring these things in and we can use them. And they become wonderful little vignettes of what the future might hold as you continue down this path. So our goal is going to be different than it would be in a traditional physics class. So in a traditional physics class where the goal is physics, we make sure that we explain the physics from ground up, right? We're not just going to give you a formula and your job is to deal with the formula. That's high school. In physics, the job is to find the formula. Usually we start with a very, very small set of kind of basic ideas, and this is one of the things that's so great about physics. We start with the smallest possible set of basic ideas about nature, and then build up from that something that we can use to solve a huge variety of problems that exist in engineering and situations that might present themselves in the laboratory. So we want to solve from small principles and then find the equation that applies to the specific case that's in the problem, right? And then the plugging the numbers is just something we do at the end. And we want to make sure we understand every step in that motivation, why the rule seems to be a good rule, can we make sense, why does this rule seem to be there and not some other? Sometimes we can make sense of that, or at least we can say it has some mathematical beauty. At least we can try to understand it intuitively. But our goal here is going to be a little bit different. I'm not going to be shy at all to just throw some big new physics idea at you and just say, this is how it is. We're just going to introduce it to you real quick. I might even give you some equations and not worry too much about where they come from because our goal is very different. Our goal on this side is actually to teach you the math, but to teach you the math as much as possible within the context of those physics examples that are relevant and that let you peek a little bit ahead into the future. So when it comes to the math side, we will be very careful. And we're going to start pretty far back. Some of you may find that we're starting a little slow. That's okay. I assure you that by the time we get to the end of the semester, it has never failed. Every single one of you will have learned a huge amount of information, a huge amount of context, and be much more confident than when you came in. Doesn't matter where we're starting from too much. And with that math, we're going to try to build it up one piece at a time. And we're always going to try to make sure when we're dealing with the math in this class that we really understand why we're doing what we're doing. Okay? We don't want to just follow rules, cookie cutter style. We don't want to follow recipes. We really want to understand what makes the math tick. And if we understand what makes the math tick, we'll be in so much better shape to do our physics in the coming semesters. Speaking to our musician, when I was in college and getting ready for college, if you had asked me to, we all kind of have identities that we classify to ourselves. I think I would have said artist and musician. I was really interested in that sort of stuff. I don't think we always realize as younger people, and it's a shame how relevant those skills are also in the sciences. The sciences are really one of the most artistic and creative arenas because we are problem solvers, and it's almost sort of a reverse of the creative process. We're trying to figure out what the world does. Okay? We're trying to make sense of it. We're trying to take this complicated world and distill it down as much as possible into the smallest set of core principles. So that's what I like so much about physics, is that it's so minimalist. And what I like so much about math is that if you do it right, you get the right answer. We're going to find out there's often lots of ways to do things, right? And that's okay. But one of the things I love so much about math is that you can know something is true without anyone ever having to have told you. Does that make sense? It's not necessarily true in physics. In physics, things can have mathematical consistency that can seem right, and it can just be that that's not how nature did it. There are a few wonderful examples in the history of physics where people sat down like Einstein or Maxwell, and they thought about how the world ought to be, and they were right. There are a few wonderful examples, but that's really the exception. But math has this beautiful property that you can absolutely know that something is true that no one ever had to tell you. That's something remarkable and unique to mathematics. Right? And what we want to do is bring you to the point that you have that confidence to design that bridge, or to build that circuit, or to calculate the curve of a highway, or whatever the career may lead you to, in a way that you know that that answer is right, that you understand the steps, how you got from point A to point B, even if you're working in an application that involves lots of computer work, which is the reality these days. We don't want people that just push the buttons on the computers. We want people that know how to write the programs that the computers run on. The people that write the programs that the computers run on have to understand what the details are behind the scenes, right? So we want to get you in contact with that kind of ground level mathematics, and we're going to build it up one piece at a time. So let's go through the syllabus a little bit further here. In short, we will be building and reviewing essential mathematical background material within the context of solving real-world physics problems. Simultaneously, we're looking to expand awareness among those students with an eye toward engineering that completing the first 3 years of physics and math at SAM forms an excellent foundation for transferring on to a dedicated engineering college. Upon completion of the course, students should have grown substantially in their ability to select the appropriate mathematical tool for specific problem applications, solve problems of exemplified type successfully and independently, explain the development of key mathematical tools from first principles, generalized concepts and example solutions to related problem variations. We also expect that you guys are hopefully going to become good friends. And over the course of a long degree, which is a grueling degree and a tough degree, you should know going in, it's important to have kind of a core group of people that you can sit down and work some problems with. Let me let you guys know that Physics Farrington 303, third floor of this building, upstairs and down the hall is your room. Go sit in there and work together on your homework. There are computers there that you can log into. There's a ping pong table there that you play around on. So that is your room to lounge in and to interact with each other and meet some of the upper division physics majors. They'll usually be happy to help you here and there if you have questions. And it's good for you guys to work together and build that camaraderie. Let's talk a little bit about tentative schedule of topics. So we're not going to follow this list to the letter. This is just sort of a sketch of one of the various ways that the course can play out. And it's going to be a list of topics that we're going to cover. Certainly most of these topics we'll cover, although the order may vary a little bit. And a list of types of example problems which could manifest that type of mathematics. And again, there will be variation there, but to give you a sense of where we're headed. We want to start off making sure that we can do our algebra. We want to start off making sure that we can solve for x and that we can rearrange our equations properly. And that's such a big problem we find that our incoming students very often have just gotten a little bit rusty in these kind of basic solve for x skills. So we're going to practice them. We're going to make sure that that core foundational skill is there. And one of the best places to do that maybe is the so-called kinematic equations. It's a good preview for your upcoming first semester physics class as well. The kinematic equations are, like, for example, what happens to a falling object or an object that's moving somehow otherwise under constant acceleration. If I know where it was and how it started, can I tell you where the thing is at in the future? So in a few minutes here, we'll write down the kinematic equations that describe that type of motion, and we'll do a few simple problems together. So that'll be one of the first sets of practicing that we're doing. Multiple dimensional motion is going to involve solving simultaneous equations. Say we have two equations and two unknowns. Can we arrange that system of equations? Free body force diagrams. This involves trigonometry. So we'll do a thorough review of our trigonometry. All of the mathematics that I'm describing, we're going to review thoroughly from ground up. Probably most of it, most of you have seen or encountered at some point, but we want to go back to the foundations and build that up again. The fact that you've seen it before let us move a little bit faster. We want to make sure that you understand it in a way that's most useful in our field. Coordinate rotations, special relativity. These are places where some matrix algebra, and in fact even some trigonometry and special relativity can be very, very relevant. Waves on a string, sinusoidal functions, circuit analysis can involve complex numbers. Remember that square root of -1 that you met somewhere along the way? You may not have realized that's actually super crazy important. It's a little hard to understand if you haven't really seen how it plays out, how important that square root of -1 is. Crazy important, important in quantum. Newton's laws in 3 dimensions, that's vectors. You've heard about magnitude and direction, right? So vectors. Work and torque, we're going to learn how to multiply vectors. That's very important. It's not obvious what that means, but we'll work out what it could mean logically, so kind of starting from the beginning. Laboratory error analysis, a little bit of statistics. We're going to learn calculus before the semester is out. How many of you have had a calculus course? And how many haven't? Okay, not to worry at all. We're going to start from the beginning. And the truth is, some of these mathematics courses that are semester long, some of them are filled with, material that we need here and here and here, and material that we don't need here and here and here. They have their own purposes for these things and their own reasons to design the courses that way, but they're not always perfectly aligned with what our needs are. So in this course, we're going to take just the bits that we need. We're going to move a little bit faster. We're going to get you ready to go. And it doesn't matter if you've seen it before or not. We're going to get everyone to get it. So differentiation, that's the process of finding the slope of a line. We know the mathematical function it describes. Very, very important. Simple harmonic motion. This is the notion of a spring with a mass attached bouncing back and forth. That may not seem very important to you, but it's maybe the most important problem in physics. Maybe. Not because we really care about springs and masses so much, but because we find out that almost everything in nature that has some sort of stabilization mechanism behaves at some level like a spring and a mass. Your body metabolism has aspects that behave in that way. Orbits of planets around the sun have aspects that behave that way. Population dynamics behave that way. Of course, any sort of mechanical system, like a car driving down a road with a shock absorber, behaves that way. Electromagnetic waves behave that way. You're going to find that some of these ideas that we explore in simple and basic contexts, once we've understood them in that basic context very well, just explode in their applicability, and that's what's exciting. Work done by position-dependent forces, good example of integration. Distance traveled for velocity versus time, good example of integration. Integration is the mathematical process of adding up something that's continuously changing. It turns out that it's the backwards of that slope finding process. We'll see what all those words mean as we look further down the road here. And towards the end of the semester, some elementary differential equations. That's a big word, but don't want to scare you. It just means equations that have rates of change in them. And up to this point, probably most of the mathematics that you've done has been very static mathematics. I remember a transition when I was taking my first calculus class in college. And up to that point, I had known that I was good at math. I could do it. It made sense to me. It never occurred to me that I liked it. Not really. But that I loved it. But when the mathematics became dynamic, when it had changes happening within the equations, when it really became clear how the things that you write down on paper are able to predict things that happen in the real world, that's a transition. I'm going to try to flip that switch for each of you this semester. Required textbook. We don't have one yet. We have tried several different textbooks over the last few years developing this course, and we haven't yet found one we're very happy with. So Professor Dent and I are writing one. And you guys are going to help us debug it a little bit. Okay? We've got about 200 pages of this thing written, and that puts us a good bit over halfway done with the text. So I'm going to be printing and handing out to you copies of the draft version of our book. You should understand it's still in development, still a little rough in places. And what we need is some feedback from you. So I'm gonna be asking you in particular, probably each week, maybe as part of our lab, to give a little bit of feedback on that week's book chapter. To read them carefully. You don't have to pay for a book, that's fantastic, but give us a little feedback so that we can make this thing great when it finally hits the shelves. Supplies, you should have a calculator. I should have brought some with me. The department just ordered a whole new batch of calculators that we're gonna use for exams. These are the TI 30X, 30XS Multiview. So they're a nifty little calculator. Now historically, what I've generally recommended are the big graphing calculators from TI, right? And if you have one of the big graphing calculators, that's perfectly fine. We'll use the smaller ones for home use. Is that what you got?
Yeah.
Oh, perfect. Oh, no, that's not.
Well, I have a graphing calculator.
Okay, let's look at both of those. Okay, so this is the XA, so slightly different. I'll tell you what I like. Oh, yeah, that's perfect, that's it. Look at that. Okay. So we got 3 calculators here. Let me tell you what I like and dislike about these calculators. Okay, so this is a pretty basic calculator. It's got most of the mathematical operations that you would need. What do we need? Well, we need our trig functions, sine, cosine, tangent, and the inverse functions. We need to be able to take logs. So this has a base 10 and a natural log. And then it can exponentiate. You can do the inverse trig functions again. Of course, it can add, subtract, and multiply and divide. That's good. Even appears to have a few kind of special statistical functions, which we don't care about too much. But let me tell you what I really dislike about this calculator. You just can't very well see what you've done. Now, let me tell you what I like about these calculators. Now, this calculator has loads and loads of functions on it, right? It'll do equation solving, matrices, and all kinds of complicated stuff. I don't care about that at all. If you want to do serious math, you shouldn't do it on a calculator. You should do it in a program like Mathematica on a computer. This device should not be used for any sort of serious mathematical application. As a matter of fact, the students at the university here at SAM, you all have access to a program called Mathematica. Have you heard of it before? It's maybe the world's greatest computer program. And I think to qualify for the label of world's greatest computer program, you also have to be yourself capable of writing programs. So Mathematica is not only a program, it's a programming language. And it's a language in which you can accomplish almost any sort of analysis of a mathematical variety and visualization of that analysis that you could imagine. It's used all the time by me and by the people I work with, and thousands of people around the world like us who do physics research. It's just wonderful. It's kind of expensive, but you have paid for it. And you can download a copy for free from the university website. So I'll provide you a link for that at some point if you can't find it. So what do I like about these calculators? All the fancy stuff they can do? No. What I like about this calculator is the display. Because where do people normally make mistakes in calculator usage? It normally has something to do with parentheses and order of operations, right? And if you're dealing with a little thing like this, you've got to kind of scribble intermediate results over on the side, you accumulate some rounding error, it's hard to group things, you can't really see everything you typed in, you might not be able to access previous answers as well. This is beautiful because it lets you see the whole thing that you typed in and make sure that it's right before you press enter, or scroll up and grab an old number. This is just a little bit bigger. It's got about 4 lines, bigger than that, bigger than that. It's got about 4 lines. You can see real clearly what you typed in. It's solar. That's really nifty, especially if we're going to have them in the department to hand out for exams. It's got all the mathematical functions you want and none of the ones you don't. And it doesn't have a memory where people can store notes in it either. We want that too. So this is a really nifty calculator. The other thing I love about it is that you can get them for less than $15 on Amazon, whereas this is $100, 80-ish. Yeah. And there are other models that are more, right? So if you have one of these, that's great. We're going to use these on exams. I'll loan you out one for the semester as long as you turn it in at the end, that's fine. Or if you want to purchase one for your personal use, that's great too. I'll bring them to class next time and you sure you're familiar with them for use on the exam. And that's what I'm excited about these new calculators. I think they look great. This was yours, and both of those were yours, right? Okay, let's talk about homework assignments a little bit. Homework assignments, we're going to have basically for each section that's covered in the course. More or less, we'll have a homework assignment per week, like you might normally expect. Now, in conjunction, what's going to be a little different is that we're going to have the in-class homework, and we're going to have the recitation lab type homework. And the recitation and the course are going to be a little bit different in style from each other. Let me tell you what I mean. So in the recitation, we're going to be more like drill time. It's going to be more a large number of problems. It's going to be a little bit more repetitive, frankly. We're going to make sure that we see lots of problems over and over that are the basic types we need to solve and get plenty of practice. Okay? And in the recitation, you'll be paired up in groups of 4, let's say. You're going to be encouraged to work with each other. And it's a great chance for you to teach each other. That's such a valuable thing. It's a great chance for you to kind of bounce off ideas from each other. In the class, we're going to tend to do work that's a little bit more sophisticated and level and kind of smaller in quantity, if that makes sense. So we'll have more applications here. We'll have more physics and engineering style context in the class. In the lab, it's going to be a little bit more straight math, a little more worksheet style, large quantity, and it's about drill, 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 and it's about you guys working together and making sure that you've got those core skills. And hopefully the combination of those two things will prove to be valuable. Regular personal application of the concepts encountered is essential to mastery of the required material. The problems, of course, are a valuable insight into what material is considered important by your instructor. Careful completion of all assignments is in itself an effective way to boost your course outcomes. So the point is this: if we're not practicing and doing the problems ourselves over and over, we haven't learned anything. Furthermore, the homework is there to boost the grade a little bit, right? It's designed that if you kind of do the homework, the grade floats up. So if we're not doing the homework, or if we're turning in homework that we just kind of copied somewhere else, then we're not going to do well on the test. And if we're not doing the homework at all, then we're not doing well on the test, and we haven't gotten the points of the homework. So that's the recipe for disaster. Be sure to do the homework. It's there to stretch you, to exercise you a little bit. And it's the only way. It's the only way to succeed on this road you select. Exams. 3 or 4. I've tried this a couple of different ways. The nice thing about 4 exams is that we can make them a little bit less dense in terms of material. It can be a little bit more trouble to fit that many exams in. 3 or 4, we'll see how our pacing's working out. Exams during the course of the semester. We'll have a comprehensive final at the end. If there's ever a special situation that exists which would cause you to miss an exam, you got to let me know that ahead of time, of course. That will be dealt with on a case-by-case basis otherwise. Grading plan. The lab, which means all of the recitation work, any of the quizzes, anything that we do in lab time. We'll have weekly assignments that are turned back in associated with the lab. They'll amount just to the leftovers of what wasn't finished at the table work session of the lab. Are each worth 20%. So 20% homework, 20% lab. The semester exams are 40%, and that leaves 20% for the final comprehensive exam. So the final comprehensive exam is weighted pretty heavily. What does that mean? It means that we expect, for people sometimes to struggle along, hopefully to keep learning, right? And to have this second chance to come back and see that material at the end of the semester and knock it out of the park. Punctual, regular attendance is expected of all class members. Absences above the level of 3 can trigger a point reduction. Class rules are pretty straightforward. All class members are expected to respect the proceedings of the course and the learning environment of their fellow students. A few basic principles. Should be academically honest. We shouldn't cheat on our tests, obviously. The truth is, I've not had too much trouble with that with my SAM students. I know and expect that you guys are all here to do your own work and to learn and to progress. I appreciate that. And you make my life easier when that's your goal. Regular punctual attendance is expected of all class members. This third one here I am pretty particular about. There should be absolutely no use of cellular phones in the class. So in fact, if the phones are actually put away, that's my preference. If you've got an emergency call, that's fine. I'll step out in the hall. I had a firefighter in my class. Of course, I've had plenty of parents in my classes. There are reasons you might need to take a call. So step out. Nothing wrong with that at all. Please don't be checking text messages during class. Email guidelines. Email communication should be made in a professional manner. Please don't send instant message style notes. Please include your name, course number, class meeting time. I've only got one boot camp, so if you say boot camp, I'll use the time. Proper salutation, body closing, business type letters. It's good practice, right? Make a reasonable attempt at correct grammar, capitalization, punctuation, and spelling. Okay. So the last page here are some tips for success, and I offer these things to, or next to the last page, the very last page is standard university policy and boilerplate. Tips for success, and I offer these to you honestly and humbly for your consideration. It sometimes is the case that the things that have made people successful in other courses, people that have been academically successful, are, it turns out, very different skills from the things that will make you a successful physics student and a successful mathematics student. So for example, there are certain disciplines in the academy where a very large amount of memorization work is important, and the classification of a huge amount of facts. And there are disciplines where that's very important. If you don't like that, I have some good news for you. Physics is not one of those disciplines. Our goal, again, is what? Smallest number of core principles, huge applicability. That's the way we think about it. That's our goal. But what it means is that the students that come in, and we find this very commonly, for example, in our biology students that come in sometimes and are taking physics for the first time, they just don't know what will make them successful in a physics class because it's a different way of thinking. And it's useful to maybe explain that explicitly at the beginning and to talk a little bit about the ways of thinking, the ways of studying, the ways of prepping that will make you successful. So some of these are more obvious. One, attend class regularly and take effective notes. That's important. The note taking is a really important skill. And you should be able to read your notes. That's important. It's certainly the case that I'll focus class time on concepts and material that I deem most valuable, beneficial, and instructive. It stands to reason that the things that we do in class are the things that are going to be on the test. You can pretty well take that to the bank. Two is really important. It's a little less obvious. Focus on ideas and concepts, not memorization. In fact, in this class, since the physics is going to be our context and the mathematics is going to be our goal, any physics equations you need, I'll provide for you. There should be no need to memorize physics equations. You may accidentally memorize a few by using them, and that's perfectly fine. Yeah, accidental memorization is the best kind of memorization. The math, on the other hand, I probably won't give you too many tips on because that's what the course is about. So the math you'll need to know. But the same principle applies. The course is fundamentally different in design than most you probably take, and retention of facts will not suffice. Success comes from what? Skillful application of the tools and logical thought processes that are developed. We're going to employ, if it were a physics class, only a short list of equations, and even in our applications, looking at physics and engineering applications, relatively short list of equations. Your job is to understand how, when, and why each of these equations, which correspond to some physical principle, is used, and how the mathematical principles are used. Complete all homework. Attempt problems individually. This is an important one. We want to stress some teamwork, especially in the lab, in the recitation period. We want you to work together. If you've got partners to work with outside of class for homework, that's fantastic. But there's a right way and a wrong way to do that. Okay? So some of my most valuable study time, I think back to graduate school, and we were preparing for our qualification exams. So our qualification exams are usually exams that you take after your first year in graduate school. And these are 4-hour exams. You take 4 of them, 16 hours test over the course of a week or so. And they occur in the kind of 4 major disciplines of our field, which are quantum mechanics, which is the subject of the sub-microscopic statistical world, thermodynamics and statistical mechanics, it's like ideal gases, other things of that variety. And classical mechanics, that's things falling or colliding or bouncing off of each other or pulling on each other. And electrodynamics, that's circuits, but it's electrical interactions, magnetic interactions, all that. So during this study process, what we did was we had sort of a group. And the fact that we had a group and that we met weekly kind of kept people accountable. But what people would do is practice all of the agreed upon problems. Since we didn't have assignments for this, it was just studies that you could pass the test, right? So we would find some questions to do, and we would agree what the questions were for that week, and you had some accountability. But you went home and you tried them yourself, and you worked on them, and you don't give up just when you push hard, right? That's a tricky one, to find the right amount of pressure. You don't want to push forever on a problem that you can't do, or that you misunderstood something back here at step 1, right? But you have to apply some pressure to these things. And once we worked hard on them, then we get back together. And maybe this person had done this 3, and this person had done some different 3, maybe had 1 in common. And maybe the 6 or 8 altogether, maybe somebody had done, and then we could teach each other. And we could fill in the gaps, and we really learned something that way. And you understood better the thing that someone else was teaching you if you had struggled with it and done it wrong first. So that's sort of the approach that I suggest to you. Attempt the problems individually, regular personal application of the concepts. Regular is important. You can't be cramming before the exam. It's got to be regular. It's the only way to go beyond understanding someone else's solution. And I hear that a lot. Well, it makes sense when you do it on the board, but then when I try to sit down and do it, I can't practice. It's a simple suggestion, but it's the only suggestion. Practice. It's the only way to develop confidence in your own problem skills and go beyond understanding someone else's solution. There's no substitute for experience from long practice. So assignments will be given for each section that we're going through, collected. Failure to participate certainly damage your test and quiz performance. These problems give insight into the exams. 4, seek out help. My office is available to you. Hours are printed there in the syllabus. It's important to persevere, to focus your attention on the problems that you can't do. But if you're just banging your head on the thing, that's not productive either. So knowing when to kind of call it, find some study partners, come see me in my office, raise your hand. We have a small group here, don't be afraid to ask during class if you've got a question. We'll find a way to back up and make a little space for it. You'll also find up in room 303 physics majors, but if you're standing around, which would be happy to help you if you have a question. Don't give up. Don't fall into that cycle where frustration blocks you from participating. I don't think any of you will, but that's a bad one to fall into. When you come to exam time, you may find a lot of questions there. Be smart, find the questions you know how to do, collect those points, use your time as best you can. We'll mostly take our exams during the recitation period, which has the advantage of giving us a little longer amount of time. This 50 minutes for an exam, I know 50 minutes can seem long sometimes, maybe now, but once that exam's handed out, 50 minutes goes quick. So we'll have a little bit of extra time during the recitations for exams, so that'll be beneficial. Keep pushing at it, don't give up. It may take a little time to learn the required way of thinking. The good news for you is that sometimes it can finally really click. And if you make that transition, you can rapidly find it's not, oh, I can do one thing. It's like, oh, I can do all the things. It's a different way of thinking. And once you have that confidence, once you've got a few foundational blocks in place, you'll find the others tip over much more easily. Last, worry less about your grade, more about developing understanding. If you're dedicated to absorbing and taking ownership, that's a big word, ownership of the material, your grade, generally speaking, is going to take care of itself. So any questions from the syllabus, expectations for the class? Okay, yeah, go ahead.
Notes are laptops.
Yeah, if you'd like to take notes on your laptops, that'll be fine, as long as that's what's happening on the laptop, I don't have any problem. And if you wanna make an audio, well, actually, we're making a recording, if you wanna make an audio recording, that's fine, but if something like that's supposed to be. No, not quite yet. Now, we will start, that's a good question, we will start probably before the rest of the physics labs start, because we're on a little bit of an isolated schedule. In fact, I need to talk to you, remind me just the last couple of minutes of class, I need to talk to you about the scheduled lab time, because the time that's scheduled is probably gonna have to be changed. We have a small enough group that may be possible, it may not be possible. We'll find a way to work it out, but I need to hold a little bit for what possible times might work.
Whenever like I signed up for the course, there was one lab time, and then later on when I actually like went in to sign up for the course again, it changed to what, Fridays?
Oh, it's listed as Friday now?
It was Thursday.
Thursday? I had two labs, so I didn't know which was which.
Okay,
but-
okay, we'll talk about it a little bit, but don't worry too much about it. We'll talk about it. Okay, I want to present to you our first problem for the semester. And we're going to introduce some equations to systemize this a little bit further ahead, but for our first problem this semester, we're going to do this in our heads. Okay. So let me present, it doesn't mean you can take notes if you want, but we're going to do it in our heads. Now let me tell you what the problem is. Okay, so let's imagine that we've got an empty well. It's offensive, it's scary. Now, so let's imagine we have an empty well and we're going to drop a rock down that well. Okay. And let's imagine that we time how long it takes that rock to get all the way down to the bottom. And our units for time are usually seconds. We're going to time how long it takes that rock to get down to the bottom of the well. But we want to figure something out based on that time. What do you think we want to figure out?
Speed.
Okay, that's a good answer. Not quite what I'm looking for.
Acceleration.
Distance. Both of these others are going to fit in, so that's good, but distance is what we're looking for. How deep is that well is the question that we want to answer. Now, to get to that answer, we're going to have to put together two things. Kind of the same two things we always have to put together when we do a problem. It's a little bit of physics, and then a whole bunch of mathematics and logic, and it's usually the prescription. The physics, the core physics of the thing is pretty simple, and it involves just one fact. It involves the rate at which objects accelerate downward when they're dropped on the surface of the earth. With a little caveat, we're going to imagine that we have no what? No wind resistance. So this problem's a little tricky, because as the rock falls, it's continuously what? Accelerating. In other words, it's speeding up. So if I knew how fast the thing was going, it would be trivial to figure out how deep the well was, right? So if I told you its speed, and I told you how long it took, you could figure out the distance. So for example, if I said I went to visit Aunt so-and-so in Dallas, let's say, okay? And I say, I'm not necessarily starting for Huntsville, I'm starting somewhere else, okay? So I start at point A to go to point B to visit Aunt so-and-so. And I say, they are 6 hours away. You guys would probably know what I meant, right, more or less? You would first imagine that I was talking about getting there by what mechanism? A car, probably, not walking. And you would imagine that in my car, I probably travel at an average of 60 miles an hour, taking stops here and there. So you might say 6 hours at 60 miles an hour, that's in the ballpark of 360 miles away, right? So you would have a sense of that. But this problem's a little trickier. Why? Now, I'm going to tell you, this problem is secretly a calculus problem. But we're going to do it without calculus. We'll understand the trick. We're pulling it better a little later in the semester. The thing that makes this thing a calculus problem, and the thing that makes it a little tricky, is that the rock is continuously speeding up, and the correct word for that is acceleration. So this is the little bit of physics. It's this little number g, which you've probably encountered somewhere before. And do you know what the value of g is?
9.8
Okay, good. And what units? That's very important.
meters per second squared.
Okay. Just for purposes of doing things in our head, I'm going to call it 10 instead of 9.8. 9.8 is close to 10. You're going to find that we like to round things, especially when rounding lets you get an estimate of something real nice and quick in your heads. Now the units here are sneaky. Meter per second squared, that's true. Have you've all heard that phrase at some point, meter per second squared? I don't know what a squared second is. To this day, I don't know. I know what a square meter is. If I go a meter this way, that's about a meter, right? A little longer than 3 feet. And a meter that way, that would be a square meter again. I have no idea what a square second is. Nevertheless, we say it a lot. I'm going to suggest to you that you can understand what that means better if you say it this way. Meters per second. Okay. So in fact, what this means is that with every second of time that passes, the object that's falling has increased its speed by about 10 meters per second. So it's 10 meters per second change in speed per second of time. So meters per second. And if you divide by something with units of seconds twice, you could say seconds squared. It's a perfectly mathematical, consistent thing to say, but it doesn't make a whole lot of sense, just conversation. So we'll continue with the normal shorthand to call that meters per second squared, but that's really what it means. Meters per second. Okay, so now let's take the next little step here. This thing fell for how long?
3 seconds.
3 seconds. And that's 3 seconds from the moment it was let go. Right? Now, the moment it was let go, how fast was it going?
0.
Okay. So from this point forward, we're not doing physics anymore, or at least not taking information directly from physics. That was the only little bit of information we needed from the world. The rest is mathematics and logic. Our initial speed is 0. After 3 seconds, how fast are we going to be going?
50 meters per second? Is it how? For what?
After 3 seconds, how fast would the rock be going?
30 meters per second.
That's right, 30. Yeah, because after 1 second, its speed has gone from 0 to 10. And then after 2 seconds, it's gone from 10 to 20. And after 3 seconds, it's gone from 20 to 30. So that's what we're saying here. Every second that passes, we pick up 10 meters per second of speed, right? Okay. So our final velocity is 30 meters per second. Let me let you in on one little shortcut here I'm pulling. I'm actually calling the down direction positive, so that I don't have to worry about negative signs. So if normally I would say that positive velocity is up and negative velocity is down. I'm just going to call the down direction positive here. So the final speed for velocity in the downward direction is 30 meters per second. Now, if you were traveling 30 meters per second for 3 seconds, how far would you have gone? 90 meters. But is that the right answer? No, because you weren't traveling 30 meters per second the whole time, right? And you certainly weren't traveling 0 the whole time. Can you think of a way to get around that? Instead of using the initial velocity or the final velocity, neither of which are correct, what's the average? You can use the average velocity. So the average velocity, what's the average velocity of this thing? 15 is right. Yeah. Should actually be a little careful there, just taking initial and final and splitting them to get an average. That works as long as it's constant acceleration. This is constant acceleration. So it works. So we weren't traveling 0 the whole time. We wouldn't have gone anywhere. And we certainly weren't traveling 30 the whole time. That's only the speed right before it struck the bottom. But halfway in between there was our average speed, which was 15. So if we went 15 meters per second on average for 3 seconds, how far did we go? 45 meters. just did our first calculus wrong. So let me switch it up a little bit. The well is 4 seconds deep. See if you can figure out how deep it is in meters.
$60 deep?
Not quite. So, after 4 seconds, our final speed is what? 40. So our average speed was 20. We went 20 meters on average per second on average for 4 seconds. We went 8 meters. Okay, last practice. 5 seconds. 125. Did everybody get 125? You. Okay. Now you know calculus. Do something else next. Okay, that's good first day. I will send you an email to kind of poll about possible lab meeting times, and I will see you back on Friday. Have a great couple of days.
Hey, does anybody want to share like phone
What
numbers?
did you say? On Friday or Thursday?
No, I'll see you back on Friday for class.
Emails.
Oh, yeah.
Just for regular class.
So we're not having lab.
No lab this week. I'll send you an email to kind of poll what the times might be for everybody.
Gonna show up.
Yeah, no lab this week. We'll just decide this week when it will begin, and we'll start next week.
Does Blackboard have all of our
Yeah,
class emails?
it does.
It does.
Okay.
Yeah. So as long as you're checking your university assigned email address, you should be
I
fine.
that one.